I will be speaking about the fundamental group of certain surfaces. So on the this is joint work with my thesis advisor. So jointly R.V. Gurjar, and so we are going to be talking about the fundamental group of certain algebraic surfaces. These algebraic surfaces happen to admit a fibration. So though it is true that the genus-2 fibrations whose fundamental group we have calculated are have certain assumptions, but I will make comments on the other things that we are yet to calculate. I mean the other surfaces in the same class. So but I will do that at the end of the talk. So let me begin by fixing some notation. So X is a over C. C will be a smooth projective curve over C, and F from X to C is a morphism of varieties such that the general fiber is a genus-2 curve. So in general the fibers can be singular, but most of them obviously will be smooth, and when they are smooth they are going to be genus-2 curves. So we are going to be working with X such that there is an F and C. So all surfaces, all complex algebraic surfaces which admit such a map to a smooth projective curve C, we are going to consider. And what are we going to ask? So the aim to calculate the fundamental group of X.
Is it always exactly the same genus-2 curve, or it varies?
You mean the complex structure? Yeah, the complex structure may vary. Yeah.
Sorry, if you do genus-1 fibrations, there is a thing that you might have to ask that there is a section. So that the generic fiber is a curve over the function field of the curve C. But that's a stronger condition than just having this map. Do you also need that? Or?
No, you don't need that. Not here. I mean.
There is some. I'm not an algebraic geometer, but there's something like multiple fibers or.
Multiple fibers, of course. See, so the thing is, multiple fibers will be considered singular, and there will be finitely many such, if there are any. So yeah, if a fiber happens to be irreducible and multiple, then we count that as singular. So there can be such. You will see. I will talk about it. But there aren't very many such. Usually they will be smooth, compact Riemann reduced.
But so you cannot think of this as a genus-2 curve over the function field of C.
Think of what as a genus-2 curve? X?
The surface as a genus-1 curve over the function field. I mean, like a generic fiber.
Well, maybe that is possible, but
I think that is this condition having a section.
I'm not sure. For instance, here some of them will not have that. So, okay. So that is the aim, and we get what we might call a bonus out of having precise information about the fundamental group of X. That is, verify application. Verify the Shaffer conjecture for X. Though I called it a bonus, it turns out that because of some work of Kolar, there is indeed a deep connection between the fundamental group and the analytic properties of this conjecture. So what this conjecture is and the statement and so on, I will do in the second half of the talk. But so let me continue with the aim, that is. So, okay, to begin with, we have this short exact sequence, H1 of F R to H1 of X R to H1 of C R. This is a fact. I mean, it's not completely trivial. So F here is the general fiber. X, of course, X and C, we know what they are. So given F, there is such a short exact sequence, and this was seen by many people. Sagar, for instance, so has a proof of this in one of his papers. The references are, I will give the references at the end. But so this sequence is there, it's given to us. And so what does this mean? Of course, it means that B1 of X is less than or equal to B1 of C plus 4, where 4 is the first Betti number of the general fiber, and you have B1C here, depending on whether it is injective or not. So we have this bound on X. So there are, of course, now three possibilities. B1 of X is equal to B1 of C, or B1 of X is equal to B1 of C plus 2, or 3. B1. So we are these three possibilities are going to be our sort of starting assumptions. We are going to ask, okay, if I want to calculate the fundamental group of X, in which of these three categories does X lie with respect to the first Betti number? So the reason why we do this is because for number 3, the answer is known, and this was done by A. Boville. So A. Boville says, Arnold Boville, A. It was in 1982, that if B1 of X is equal to B1 of C plus 4, then X is birational to the product F cross C. So it's birational. That's what he proves in an appendix to a paper by Debar, and it's not very hard to see that this actually implies an isomorphism. I will not go into that detail, but in fact it is an isomorphism, in which case of course the fundamental group is the, so hence pi 1 of x is pi 1 of f times pi 1 of c. So we know the answer for 3.
But does birational always change the fundamental?
No. I mean, but I just wanted to point out that it is in fact isomorphism. So yeah, so this is so we know what the answer is in case 3. So our paper deals with case 2. Case 1, some of the examples are still open. We have not been able to do that, but case 2 we have now resolved, and let me then state sort of the main theorem of this talk. So okay, or should I? Yeah, okay. So theorem. Let f from x to c be a relatively minimal Genus-2 fibration on x smooth projective suppose that b1 of x is equal to b1 of c plus 2, then we have the following assertions. Right. Also, I'm assuming that there is at least one singular fiber. When there are no singular fibers, there is some work by Fabrizio Catanese on these type of surfaces, which comments on the fundamental group. But here we are going to assume that it's not C infinity. There is some singular fiber, and yeah. So assume. Have I say okay? Assertions. So if f has a degenerate fiber, then
that means that map f is not local. What is the meaning of having a degenerate fiber?
It means that at least one fiber is not a curve of smooth projective curve of Genus-2.
Reduced.
Well, it may be reduced and still not. It may be. It may not even be irreducible. So it could be some union of rational curves, for instance.
It's still a nice smooth Genus-2 curve, but this curve is.
That cannot happen.
That cannot happen.
That cannot happen. It's just the adjunction formula if you apply, because f square, the self-intersection of the fiber is 0. So if you just apply, the genus has to match, arithmetic genus and topological genus. So yeah. So then pi 1 of x is one of the following. Pi 1 of x is isomorphic to pi 1 of c times z direct sum z, or pi 1 of x is isomorphic to gamma 1 times z direct sum z, where gamma 1 is a quotient of some fundamental group of a compact Riemann surface. So it may seem a little mysterious right now, but I will explain when I'm explaining the strategy of the proof what compact Riemann surface this will be. So it's a Fuchsian group, that's what we can say. So in summary, the fundamental group is always a product, and one of the factors is always the fundamental group of an elliptic curve. Sometimes it is the fundamental group of the base is the other factor, or sometimes it's gamma 1, which is actually so we will know what group this thing is a quotient of. That we can answer in the proof. We can see that. So this is sort of the theorem. This is the theorem. And so how do we go about proving this? Of course, I'm not going to give the full proof because it's very long and technical, and maybe it's not a good idea. 1 hour is not enough. But I will give us sort of a sketch of what goes into it. So I suppose I can rub this panel now, I think.
Well, you can use that one.
Oh, okay. So, so we have, of course, we have the exact sequence alb f to alb x this sequence is the induced sequence of abelian varieties, and because b1 of x is b1 of c plus 2, this the image, so the image a alb f image of the map is one dimension. Because the dimension of the Albanese is half the first Betti number, and the question is, I mean, will it drop or not? I mean, so if it becomes 0, let's say here, then this dimension and this dimension are the same. But that's not true, because you can see it's, by assumption, it's not h twice that is not the same, so half that cannot be the same. So which means that this does sort of map to abelian variety of dimension 1. So so we will denote that abelian variety. So denote this image by E. So E is an elliptic curve sitting inside alb x, and there is so there is a theorem by Poincaré. It says that if in an abelian variety you have some subvariety, so abelian subvariety, then there is another abelian variety which is transverse to this one. In our case, this is a curve, and there is another h, let's say, which is transverse with only like finitely many points in common, and h together with E will generate the whole abelian variety. So that you can always do. It's a theorem. So corresponding to this E of ours, there is an h, and we go modulo h. We take the quotient of alb x modulo h. So so by theorem there exists an H such that H intersection E is finite, and H times E generate is equal to X. So now consider the quotient alb X mod H.
You assume that you have to choose base points everywhere.
You have to choose base points.
Yeah, you do. Or just you assume that there is a base point.
But why do we need that?
No, I'm just asking you because the quotient here is, are you taking the quotient in the sense of group or like taking it logical space?
No, I'm taking it in the sense of groups.
Okay. So
Yeah.
you just have to space for me, okay?
Yeah. So alb X mod H, of course, the image is going to be one dimensional, and it's going to be an elliptic curve, which we will again denote by E because we have no business with this E now. We don't use it. So to E. Okay, so we have an elliptic curve here. It sort of come because of this beta 1 X being equal to beta 1 C plus 2. Because you got that because of the condition. So, but of course, from X to alb X, we have a map, and from alb X to alb X mod H equal to E, we have a map, which means that we actually have a map from X to an elliptic curve. So now we have two maps. One is the map F from X to C, and the other is the map, let's say G from X to E. There is a special property that this map has just by the construction, and that is fibers fibers of F map onto. So what I'm saying is that you take this X to C, we have this map F, and you consider a fiber like this, and you see its image. It's not going to go to a point. That will never happen. And why is that? Well, it's X to C. This commutes, and F goes to a point here, which means that so F is the fiber. F goes to a point here, which means that F, when you bring F here, it has to go to a point here, which means that F is in the kernel of this map alb X to alb C, which means, of course, that it is not, it is in the kernel, which means that it's sort of, what am I saying?
It's in E.
Yeah, it's in E. So yeah, so therefore F is going to map to. So yeah, okay. So this is sort of. Okay, so now to summarize, I think now I have to go there. So what has happened here? So hence we have two maps, X, F from X to C, and G from X to E, and therefore we have G from to C curves. So we have a map from X to another surface, which is, I mean, fairly simple. We understand what this is, and the idea is to show that the fundamental group at the level of the fundamental groups, F cross G actually induces an isomorphism. I mean, of course, not always, because otherwise there wouldn't be two possibilities, but it can sort of, in most cases it happens, and in the cases when it does not happen, you get the other option. So this is the sort of the philosophy. I mean, this is a guess, and so let's see why there are two cases. So you have this X. So I'm going to draw a few fibers. This is the C, this is the map F, and this is F cross G to these are all elliptic curves, and again C, and this is a projection. Now the question is, so okay, first of all, of course this map is generically finite. I mean, most of the times it is finite, but there will be maybe some curves will contract. So what is the degree? Well, it turns out that the degree is 2. This is like the main lemma. Once you prove this lemma, then most of the things are settled. But the question is, okay, the degree is 2, what happens to the ramification divisor? So the ramification divisor, I mean, by the Riemann-Hurwitz formula, this is a genus-2 curve and this is genus-1. So there are going to be 2 points of ramification, or there can be one with ramification index 3, but that case can be ruled out. So you have 2 points of ramification, and the question is, so let me, this warrants another panel, I think. So question?
Sorry, is there some reason why this degree is 2?
Yes, of course. But I mean, it's a lemma.
But what's the degree here of the fibers, the map from the fibers of F to E?
It is 2.
So not a coincidence, right?
No, it's the same map. Yeah, it's not a coincidence, but it's not easy to see.
Okay.
That's all.
This one.
Yeah.
To show this one.
Yeah, it's not easy to see. Yeah. So, yeah, it's not easy. But so what is the nature of the ramification locus of F cross G? Before we even ask what is the degree, we have to ask what is the nature of the ramification locus, because the number of possible ramification points is sort of okay, well, maybe first we have to prove degree 2. Anyway, so
sorry, maybe my question is very stupid.
I mean, there are always 2 ramification points. If you cover from genus-2 to genus-1, the degree doesn't matter.
Yeah, of course. Yeah, you're right. Genus-1, yes, it does. Yeah.
But the Hurwitz formula doesn't bound the degree. That's why.
Yeah. Sorry.
Yeah. The degree could be anything.
Yeah. You're right. Sorry. Yeah. Okay. Yeah. So yes. So that is why we ask what is the nature? What is the nature in the sense that is the ramification divisor one irreducible curve, or is it two different? Is it a union of two disjoint sections of the fibration. So it turns out that both can be possible, and if it is if it is a disjoint union, if it is a union of two irreducible sections, then the first thing happens, and if it is not, then the second. So 1, R is irreducible, and second, R is not. So it turns out that when R is not, well, this is not so hard to see, that when R is not irreducible, the two disjoint sections, the two sections are going to be disjoint, because if they are not, then there is a singularity in the ramification locus, and for a map of degree 2, the ramification locus is always smooth. So this can be seen. So when R is not irreducible, then the ramification locus is actually two disjoint sections, and when it is irreducible, then of course it's a two section, and it is also smooth. You can show that. I mean, it's smooth because it's degree 2 again. So these two possibilities sort of give these two possibilities for the fundamental group. So having sort of given an idea of what goes into the proof and why these two, oh, by the way, so gamma 1 is a quotient of the fundamental group of R. Also note, gamma 1 is in so this is something I should sort of mention, and so this sort of completes the first half of the lecture, where I explain, sort of give a survey of the result, and now I will go on to well, maybe I should spend a little more time, because so the question you can ask is, okay, so why do you get an elliptic curve for the fundamental group? I mean, one of the factors is z directs from z. Pi 1 of x is something times z directs from z. Where does this elliptic curve come from? Of course, it is, I mean, partially it is because you have these elliptic curves here, but you have to consider what singular fibers can occur in a genus 2 fibration when beta 1 of x is so the singular fibers play an important role in the proof, and so there is so Namikawa, Ueno and Og have classified all singular fibers of F. We know all the possibilities that can occur in the case of a singular fiber of a genus 2 fibration.
But
It's
fiber is, you have a 2-to-1 map from genus 2 to E.
Yeah.
That makes maybe help a lot to classify the singular fibers.
Sorry, that?
That helps a lot to classify your singular fiber.
Yes. I mean, we know that there is a large list. There are 44 different types. But what can possibly happen? Because you have a map from the singular fiber to, it's a non-constant map from a singular fiber to an elliptic curve. So obviously not all the components are going to be rational. So it turns out that in the classification of singular fibers for genus-2 fibrations, most of the fibers are trees of rational curves, and they are not going to occur here, right? So already, because we have that map E from X, we have that map G from X to E with fibers mapping in a non-constant fashion to E, many fibers are eliminated. So we have to consider only those fibers where at least one of the component is non-rational. So it turns out that the highest genus that the irreducible component can sort of take is 1, elliptic curves. So elliptic curves occur in the following way: 2 elliptic curves with a chain of rational curves connecting them, all with self-intersection -2, or you have 1 elliptic curve with a nodal singularity, or you have 1 elliptic curve and a chain of -2 curves. These are the only possibilities. There is one possibility of elliptic curve with a cusp, but that cannot occur because a cuspidal elliptic curve cannot map in a non-constant fashion to a smooth elliptic curve. Because if you resolve it, then you get another elliptic curve with just one point above this, and between 2 elliptic curves the map is locally an isomorphism, but this, I mean, there is no isomorphism from here to here. So that possibility is also eliminated. So this is so immediately after we realize that there is a map to E, we come to this conclusion that the number of singular fibers is really restricted. Okay, and these are the only ones possible. Notice that wherever there is a rational curve, it's always a chain, a linear chain. That helps because when you contract a linear chain of rational curves, you get a simple singularity. And we need the explicit equation of the singularity to prove that the map is degree 2. So we managed to verify things because we have this linear chain or this linear chain or nothing at all.
So which you do it first? You first prove degree 2 and then classify?
No. First classify all the singular fibers that can occur. Then you use this. You see, because what happens is that you have this map from X to C cross E, but it's only generically finite. All the rational curves are going to be contracted. So it factors through a surface Z, where now from Z to E, C cross E, it is actually finite. But Z will have singularities. That is those obtained by contracting these chains of rational curves. Is that clear? I mean, it's basically this is a proper map and this is a finite map. So I mean, so it turns out that having rational, I mean, simple singularities on Z will help us. Yeah, actually I should have stated this statement before I went to maybe the nature of R, but yeah, so that is the thing. Yeah.
What is ramification locus? Can I think of this as some sort of curve covering the base curve C?
Yes, it does. I mean, that among other things it is also that, but it's basically
degree or the genus, or
it's 2. The degree of the map
is 2.
Yes, it's 2. You see, because the ramification points are 2, no? So I mean, it is meeting every curve, every fiber twice. So the map to the base is going to be degree 2 from the ramification locus.
Yeah, but basically this is the same. I mean, proving degree 2 or proving 2 ramification point on each fiber is basically the same. So how to approach the?
No. I think what he was asking was what is the degree what is the degree of F when you restrict it to the ramification locus.
Okay. So, but still, this picture does not imply, degree 2.
No, it doesn't.
Yeah.
No, it doesn't. The point, so what I'm trying to say is that it helps to have only these singular fibers. And one of the points is that these singularities induced by these chains of -2 curves are simple. So we know the explicit equation of the singularity, and that goes a long way in the proof that it is a degree 2 map. I mean, this is far from the proof, but it's important that I mention the role of singular fibers in the proof. I mean, this is where the fibers help us. So this is about the theorem, and now I'm going to talk about the conjecture of Shafarevich. So the conjecture. So let X be a smooth projective variety over C. Then the vertical space X tilde of X and what does so covering spaces of universal covering spaces of smooth projective varieties over C are holomorphically convex. That is the conjecture. So let me explain what holomorphically convex means. On U such that mod so given any sequence of points on a complex manifold without a limit point, there is a holomorphic function on that manifold which is unbounded on the sequence. Then if the manifold has this property, then it is said to be holomorphically convex. And what the conjecture says is that universal covering spaces of smooth projective varieties always have this property. So maybe a little bit of history first. Of what has been done. So of course a lot has been done for this conjecture, but I will only state the few results that are related to what we are doing here. So theorem. This is due to Gurjar and Shastri. So what does it say? For and the Shafarevich conjecture is true. So if you have a genus-2 fibration here, similarly we can have surfaces that admit a fibration such that the general fiber is an elliptic curve, and in that case the Shafarevich conjecture is true. And they do this by proving the following.
This is in dimension 2. It's an elliptic curve. This elliptic surface.
Yeah. Sorry, I didn't get your question.
This theorem concerns surfaces.
Yes. It was not. Yeah. Sorry. Yeah, the elliptic fibration means x. Yeah, surface. Yeah. So what? F from x to C, elliptic fibration. Dimension x equal to 2. F general fiber. Then pi 1 of f to pi 1 of x has finite image. They first prove this result, and then using this fact they verify the Shafarevich conjecture. How they do it? Well, I'm going to demonstrate how we can verify the Shafarevich conjecture for genus-2 fibrations using our information about the fundamental group. So that will give some spirit of the proof of this, how this fact implies the Shafarevich conjecture for elliptic fibrations. So note that when you have verified the Shafarevich conjecture for elliptic fibrations, you have verified it for all surfaces which are not of general type, meaning that the Kodaira dimension is lesser or equal to 1, because they are all either elliptic or they are ruled surfaces, or P2. So for ruled surfaces also it's not very hard to see this sort of a thing.
Is it good for K3
K3 surfaces, yeah, I think so. But won't they have but won't they come with a fibration elliptic?
Only some are elliptic.
And what about the others? Won't they have a ruling?
I don't think so.
No? Okay.
I mean, if it's not general and it's not doesn't have an elliptic fibration, then it should be rational K3, or I think that's essentially it. Or maybe a ruling.
Okay, so well, I'm not sure. So about K3, but
maybe it's proved.
yeah, maybe. So yeah, it has finite image. That's the that was proved. This fact was proved in 1985, and then a similar fact was proved for hyperelliptic fibrations with irreducible singular fibers. So if you have a hyperelliptic fibration with irreducible degenerate fibers, then this again holds, and so you can prove the Shafarevich conjecture for those surfaces also. This was also done by Gurjar, Paul, and Purna Prajna. This was done recently in 2011. So these are the sort of results in this direction, and now I will demonstrate partially how we can go about proving the Shafarevich conjecture in our case. So we are going to take only that case when X to C cross E, there is an isomorphism at the level of fundamental groups. Pi 1x is isomorphic to C cross. So one of the cases is this, and we are going to assume this just because the other one will be slightly again technical. So okay, we have this space of two compact Riemann surfaces. Of course, it's U times C is the universal cover, where U is a Riemann surface, and it was shown by Narasimhan that U is holomorphically convex. The cover of a compact Riemann surface is holomorphically convex. This was shown, and of course C is holomorphically convex, so the product is holomorphically convex. Now we take the fibered product X tilde. This is a covering by assumption, and hence this is a covering. We know that can be shown. But the question is this a universal cover? Well, it is, because if X is a non-trivial element of the fundamental group of X tilde, then at the level of fundamental groups, this map is an injection.
Excuse me, how was X tilde defined?
It's defined as a fibered product of X and this space over C cross E. So X maps injectively into the fundamental group of X, and because there is an isomorphism between these two fundamental groups, X will map to X tilde, which is non-zero. But if you go from here to here, this is they have trivial fundamental groups, so X is going to go to 0 and will go to 0, but that's a contradiction. So X cannot be non-zero. So X tilde indeed has trivial fundamental group. Now you have X tilde and you have a map to U cross C, but this map is proper because it is a base change of this proper map. Once you have a proper map to a holomorphically convex space, this will also be holomorphically convex. Why? Because you take any sequence here without limit points, you map it here, it's going to be another sequence without limit points. That's the definition of a proper map. And here you have a function f on the image sequence which is unbounded. Now you take you compose that holomorphic function with this map, and you get an unbounded holomorphic function on X tilde. So that way we prove that X tilde is holomorphically convex. And as a result, some time ago Gurjar had shown that if X has so this is due to Gurjar, if X has a if X has HC X tilde, then pi 2 of X is torsion free abelian. If X has a holomorphically convex universal cover, then the second homotopy group of X is torsion free abelian. This was shown by Gurjar, I think, in 2004. So because we have proved the Shafarevich conjecture for these genus-2 fibrations, we also know about the second homotopy group of X. Yeah, I think yes, I should comment on the first case. So So this is about whatever I said was about B1x is equal to B1c plus 2. B1x is equal to c plus 2. This was our assumption. Now the question is, what about B1x equal to B1c? So there is a sequence due to Nori. Pi 1 of f is of x. This is due to Nori. When x has a fibration like this, which is not C infinity, then you can say this. This was proved by Nori in one paper some time ago, many years ago. So it turns out that most singular fibers of the genus-2 fibration have trivial fundamental group, in the sense that they are trees of rational curves, in which case this vanishes. So pi 1x becomes isomorphic to pi 1c. So mostly we know what happens, but that's not enough, because there are examples of singular fibers which are like this. So rational curve with 2 nodes, or something like this, rational curves meeting in some funny way, and these can occur. So in these cases we don't know what to do yet, because we don't have the auxiliary map to E, and that map to E was very helpful. It gave us so much information, but in this case we don't know. When we tried to prove the conjecture for these cases, we were naturally led into very group theoretic questions, like about free groups and the star product of free groups and so on, and very combinatorial in nature, but we were not able to handle those cases. And I think the fact that we were led to those questions is no coincidence, because there is a paper of Bogomolov in the 97 maybe, where he is proposing a way to find a counterexample to the Shafarevich conjecture, and he proposes a problem in group theory, which if solved will mean that the Shafarevich conjecture is not true. But it seems that that problem in group theory is not a verifiable statement, so it's harder to disprove than prove. So I think that sort of has died down, but the fact that we were naturally led into group theoretic problems is some indication that maybe, since we have concrete examples here to work with, we might find some counterexample, but we don't know.
Rational curve with 2 nodes?
Yeah.
And then is the fundamental group trivial?
No.
What is the
with 2 nodes, what will it mean? Will it mean 3 spheres wedged at 2 points? I'm not sure. Yeah, what is a fundamental group of such a thing?
Second example is two rational spheres forming like a small cycle.
Yeah, forming a cycle. But and not just one cycle. Sometimes there are some more complicated fibers which have 2 loops and so on. So the challenge is to find out what happens to the image. Pi 1 of f, how does it sit inside pi 1 of x? Unless we know, and it is not finite, we know that. So, and how do we go about it? That's the problem. If you knew that, then yeah, but anyway, I think.
So in general, surface usually has fundamental group has a torsion group, but in your theorem, it does not have any torsion group.
Yeah, I didn't know that this.
What's the reason here?
I'm not so. For instance, I didn't know what you just said. That in general, that it has.
No. I mean, there are many examples which has a torsion.
I see.
Torsion group in fundamental groups, but.
I suppose. I mean, see. The reason why we were led to considering genus-2 fibrations at all is that pi1f to pi1x does not have finite image for these things. So when this result was being presented at some conference, Katanese came up with a counter example for genus-2 fibrations, which is why we got interested in the question of proving these things for genus-2 fibrations in the first place. So maybe that is sort of the root of these fundamental groups. I mean, this thing does not. This is sort of. This is a very like it's a common condition when trying to talk about the Schaffer-Witch conjecture. So there's a paper of Kolar which says that there always, given a surface X, there always exists a surface SH of X with a map SHX such that the fibers are connected, and mostly the codimension 1 subvarieties, the pi1 the image is finite, I think, some such thing. So this is very fundamental to the study of the conjecture, and because this failed, we started working on genus-2 fibrations. Now maybe it's all the fact that there's no torsion stems from such considerations.
And I have one more question. So, is it true if there is a finite map from two surfaces x to y, and if the Schaffer-Witch conjecture holds for y?
Yeah.
Is it true also Schaffer-Witch conjecture?
Yeah, it's a result of Stein.
So these are basically coming then.
Yeah. It's the other way we use when the R is irreducible. So you need that. This is easy, but the other way. So we need that lemma of Stein, which says that x to y proper, then x Stein if and only if y Stein.
So actually, in this proof, you do not need a degree 2, I mean just any finite.
Yeah. But to compute the fundamental group, you need degree 2.
I have a question about the three cases for the B1 of X.
Mm-hmm.
The B1 of X is maxima when it's a product.
Yeah.
The surface is a product. And you looked at this case, but you assume that one fiber is singular. So it means this is why the part of the fundamental group of the fiber disappears, right? At the singular fiber.
Yes.
But you also say that there are some cases where this is true, but all the fibers are smooth.
Yeah.
Right. Can you say more on this?
No, because I have not seen that work of Katanese.
Okay.
But recently he communicated this to my thesis advisor, that he has a paper, but I'm not sure of the contents of that paper.
Okay.
Yeah, but you can. It's a recent paper, and it's by Katanese, so you can look it up. I think. Yeah, it helps to have the singular fiber for us. If you don't have a singular fiber, you can still verify the conjecture of Schaffer-Witch, but you cannot say. I mean, you can say, but that has been said by Katanese about the fundamental group. Yeah.
So if you think of this surface as you take the function field of the base curve C and you take a genus-2 curve over that, then you just spread it out.
Yeah.
So if you assume, I mean, this is a genus-2 curve, so it has the hyperelliptic involution. If you assume it has another involution, the quotient would be an elliptic.
If you assume that it has another involution, yes.
The quotient would be an elliptic curve.
Yeah.
And then you would have this genus-2 vibration, and in between you would have this elliptic vibration.
In between you would have, by in between you mean?
I mean, so you map from the generic genus-2 curve to a quotient, which is
no, X to C you have a map, that's okay. You're starting with this. This is genus-2. Is that how you're doing it? This is given, right? F?
Yeah, no, this is one. Yeah, but now the X has a map to an E.
I see. With
this E, and this E also maps to, no, this may be a different P1 or a bit different.
Yeah, well,
oh, yeah, I mean,
I think if you see, because it's hyperelliptic and because of that generic involution, there is a map from X to a ruled surface. I mean, each genus-2 curve is going to have a map to a rational curve, and this sort of can be glued together to from X to a ruled surface, and that also can be used, but that I mean, it's not sufficient for our purposes. I mean, the map is not degree 2 first of all, and of course the pi 1 of this is just pi 1 of C, so it doesn't.
No, but this elliptic curve would also be an elliptic curve over the function field of C. So
yes.
So you have a degree 2 map to an elliptic vibration.
No, that is the part I'm not getting. How if you get that, if you get an elliptic curve, then I think
if you assume you have this X bar involution on the generic fiber.
I see, and you're sure that that is not the same thing as B1 X is B1 C plus 2? I mean, I'm not sure about that. I mean, extra involution and this, if they are not the same, then that's great. But I mean, if it is the same, then.
So what do you mean, this difference too? I mean,
this
difference.
Yeah, this thing.
This difference too, I think, implies that you have this
extra involution.
Yeah, or this elliptic.
Okay.
But if you have that, maybe you can still have difference 4 or 0.
If it's 0, that's great. But can you?
No, yeah, I'm just.
I don't know. I mean, if that's.
But one has the feeling that should be helpful because you have this elliptic vibration which also spreads out and sort of is.
Yeah, sure. No, it's certainly helpful if you know the difference is great. I mean, 0, let's say. If you still have an extra involution and the difference is 0, then of course, because the same thing will go through, you see, because the fibers are mapping onto the E, so the same restriction on the singular fibers will come, and then by what, I mean, how we have proved it, it all goes through. But we have to have that. But you see,
the classification does not completely go through because the fibers of this elliptic vibration might somewhere be singular.
Oh, I see. Oh, it's just an elliptic vibration. I see. Yeah. In fact,
also have singular fibers.
Yeah. In fact, if the difference is 0, then you cannot. I mean, the vibration will have singular fibers, because otherwise, I mean, the classification of singular fibers says that all the fibers do occur in a. I mean, so the rational, the trees of rational curves will simply not occur if it's just a, C infinity. So. Yeah, but still it may be helpful, I mean, what you're saying. But one has to answer, I mean, if you assume that there is that extra involution, then what bearing does it have on the difference? That if we can answer, then maybe we can push it a little bit more. Yeah.
If there is any other question, let's thank the speaker.
Thank you.